some people don't like the pencil sharpener that's missing part of the handle.
I was trying to figure out.
Yeah, the electric one should be working.
No.
Plugged in.
No, it's not.
You just want to make it as complicated as possible. Pardon? Man. I apologize. Remind me at the break, I'll go take a look, just to see if I can figure out why I missed it.
Okay. You George Fox?
George Fox.
That's you?
Yeah. You're the new Tony Steele.
Huh?
Student I had a number of years ago, Tony Steele. For some reason, I would always miss his emails.
Oh.
And then he'd tell me about it, and I go and look and go, well, there they are. But it's consistently, Tony Steele, I keep missing. So, the new Tony Steele.
Oh.
I hope it won't be like that. For him, it was the entire 2 semesters of always missing his emails.
Well, I hope I'll be a little different.
All right, I'm sorry, I definitely oversight on my part. All right, start out with any questions.
The question that I do have, we can say that for the end of the class.
Okay. Or in the middle of it, you feel inspired, and just want to shout it out. It seems like we last left off, I just put F down up on the board. Was that the last thing we did, or was that a different class? What was the last thing we did?
Yeah.
Okay. So recapping some of that. In essence, this is a checklist. Whenever you're looking at a situation, you need to analyze it. Because again, it's all about predicting the future. And one of the things that affects the way things move are forces, which is what we're doing in chapter 2. Chapter 3, we talk about, if you know what the acceleration is, how do you actually sort of predict what's going to happen? And then in chapter 4, we connect forces and acceleration, even though I'll do some of it here and some of it in chapter 3. But to analyze the situation, we need to figure out what forces are actually involved, and so that's what this is. So this is some recap here. This is friction, tension, other, weight. And I'm going to put in parentheses here, even though it is weight, it's also, will expand when we get to chapter 9, I think it is, gravitational force in general. It's called weight when you are near the surface of a planet or moon, and if you're talking about the force between a planet and the sun, you generally don't call it weight at that point. And N for normal. There we go, that's the right one. What do we get? Let me see your notes, let's see how far I actually got. I did the symbol and then that one, okay. So the symbol I use for friction is sort of a curve F for tension. And I probably mentioned last time I used capital T, but later on we will use a formula that has period in it, which we use a capital T, and tension. And so I'll just go ahead and try to break myself from using a capital T at this point. This is problem specific, or problem dependent. And for weight, I use a lowercase w. For gravitational force, I'll use F sub g. That's a subscript g. And for normal force, actually, I use the letter y. All right, the thing that I did skip over last time is requirements. So as you're looking at a situation, how do you know whether a force is even at play or not, much less where it's acting and in what direction? So for friction, there needs to be contact. And there needs to be desired relative motion. So if I have a perfectly level surface and I put a box on it, it doesn't have any desire to slide one way or the other. There's no friction involved. It's only when it wants to move this friction kick in. Now it doesn't actually have to move to have friction on it. For instance, I can push on this table right here and it's not sliding because friction is stopping it. So, but it desires to. If the floor were frictionless, this table would move. And the relative piece of it will definitely come in. Well, before the end of the day. Tension requires a taut rope, chain, string, whatever happens to be pulling. The requirement is we don't know or care intellectually. The source. And the reason it's problem dependent is the fact that it'd be stated in the problem, a 5 Newton force pushes on a box. I'm not stating what's causing that 5 Newton force, it's there. That's an example of other. Gravitational force, let's do the general one first, requires 2 masses. There's a gravitational force between you and the book in front of you, between you and the table, between you and the ceiling, between you and every person in this room. It's really tiny, so we will ignore gravitational force until we deal with really huge objects. Weight is a specific case of this, so it does require 2 masses, but it also requires 1 small mass near 1 huge mass. And huge, I'm talking about planet, moon, something of that size, sun. Small is anything small in comparison to that huge mass. An elephant would be considered a small mass in this case. And normal force requires contact. We will definitely be going into more detail on this. As I take you through the ever exciting journey of boxes and ground. Oh yeah, it does get that exciting. I did before direction relative to object or direction relative to, I think I did object last time.
Yes.
Okay. Direction relative to objects. All forces require 2 objects. So friction is parallel to surfaces of contact. chances these markers still work. Come back to life. Tension is along the line of the taut rope, chain, string, whatever happens to be tight. So in the example in the hallway, when the people in the inn were pulling on it, the tension was going along, straight along, parallel to the rope. Other problem dependent. The problem will tell you the direction of that force. Weight toward center of mass of other object. And I think the example I did last time is my weight is a force that is acting towards whatever is causing my weight. In this case, the earth is pointing towards the center of mass of the earth. Likewise, I'm pulling up on the earth, it is pointing towards my center of mass. And the normal perpendicular to surfaces of contact. And I realize I'm just throwing stuff at you right now. Don't worry, we'll do the application in just a moment. I'm just trying to get some basic stuff down. Questions? Some people are still writing here. A couple more minutes for people to finish. Then direction of pair. There are not a lot of times in physics where you can get away with actually saying always. There's a whole lot of 99% of the time rules, but always doesn't happen a lot. Forces always happen in pairs. One of the few always. When you write that down, that's important enough to remember. Forces always happen in pairs. And each force of that pair acts opposite to each other. Each force acts opposite to the other. So when I do my force diagrams, when I start looking at the forces, whatever force, if I put a force going this way, there's going to be another force going that way. One's going this way, there's another one going that way. They will always point in opposite directions. The exception of what you write down is in the case of other, when you don't know what's causing it, you generally don't write that down. But it's still there. So if I'm talking about friction, the pair of friction forces will always be anti-parallel to each other. They're side by side, pointing in opposite directions. Whether it's horizontal or vertical or at some strange angle, it's just they're always anti-parallel to each other. A pair of tensions will always point towards each other. Other, again, you don't know what's causing the force, and so typically, or it's irrelevant what's causing the force, you generally don't write those down. So not applicable. Weight. That pair of forces is always acting towards each other. So typically vertically, but they're pointing towards each other. And normal force, the pair always points away from each other. So as we go through the next series of examples, we sort of keep flipping back and forth just to sort of reinforce some of the stuff that's been written down here. Questions up to here?
What was that word saying underneath force? Each force what? The pair?
Here?
No, over to your right. Each force.
Each force of the pair
Oh.
acts opposite to the other.
Thank you.
Setting up for when I draw my arrows over here, they're in opposite directions.
Why do you have a volleyball right there?
Where should it be? Does it bother you?
No, I like volleyball.
It's always impossible. I hope that's not focusing on the volleyball. I remember if I mentioned this class or the other class, I do have an entire class recorded, and the whole thing is blurry because it's focusing on the wrong thing. All right, other questions? All right, so let's actually apply this stuff. Got all that stuff written down, or at least enough of it. Leave that up until somebody's still trying to get through that. All right, here we go. This first one's exciting. Box falling. Yeah, that's right. So first off, whenever you're given a problem, my recommendation is you draw a picture. Now, some people can visualize the whole thing in their heads, and more power to you. But I recommend drawing it down. So I'm going to, the hash mark right here indicating something that's fixed. So this is the ground. And if in doubt, you can just always write down the ground. And then I have box. Now we are going to ignore air resistance. Notice that is not part of our checklist of F-town, but I am going to put little streams here to indicate that this thing is falling, not that it's smelling. When we do a force diagram, the first thing I recommend that you do is you draw the objects separate. Now in this particular case, they're already separate. The box is falling down. It's not on the ground, it's falling. But as a matter of habit, I'm going to draw the two objects over here, and this is where I'm going to draw my arrows. One of the biggest rookie mistakes that I see are people who draw things, they don't give themselves enough space for drawing. I'm going to give myself slightly more space there. And so now we go down the checklist. Is there anything we can eliminate? Any of the 5 things there that we know are not going to be involved in this problem? Why is other not part of it? What was that?
I said I just made a guess.
Oh.
It seemed like it's never in anything, so.
They tend to show up in textbook problems. You're right, other's not there, but what's the big clue that other is not involved here?
There's problems with it?
And?
Don't know what they're.
It technically tells you what's happening.
And?
We know the direction of pair of forces.
Not that. If other had been involved, what would you have expected?
Is something specific?
You give me an example of something that would have made you realize, oh, others involved.
What was it? We don't know the source of it?
Not that. I think it's devolved into a mind reading exercise. So let's explain more. And some of you might have said this, or you've been thinking this, and I apologize. Others not involved because I did not say that there's an additional force involved here. I didn't give some mysterious, there's an additional 5 Newton force acting on the box. In order for other to be involved, I need to supply you with some mystery force. So other, gone. Just like that. What else is not going to be in this problem?
Tension,
Why not?
because there's no rope, chain, or something that is.
Gone. Anything else we can get rid of?
That's why, I don't know why you wrote that. The F-town, I didn't know why you wrote that, but now I know.
Okay. Yeah, it's my checklist. I find that when I do it free form, I got something more complex and I just sort of goes through my head. Inevitably, I'm gonna forget something, so that's why I write it down.
So can we take off weight?
Say it again?
Weight?
It's not gonna be there?
No.
Do we have a small object and a huge object?
Weight of the box, though.
Going towards the earth.
Yeah, weight is involved.
Okay.
Because ground we assume is part of a planet. We are making that assumption. And box is small compared to it. We assume that the box is close enough to the surface.
Okay.
It would be normal, cause there's not another mass next to it.
More specifically, not a matter of, not just that it's not,
There's not a huge mass, there's a small mass, which is the box that's not next to a huge mass,
when you say next to, what do you mean?
like near it.
And the normal force has one other, it's not just near for normal force.
So it's going
Is
towards
it
each other?
Uh, Perpendicular,
What's the requirement for normal force to exist?
Needs contact.
Yes,
It needs what?
contact.
Oh.
It's not just whether something's near it or not, it's whether something is touching it or not. Box is not touching the ground, so normal force is gone. Likewise, there's no contact, friction is gone. So now we're back to what